We are going to look at Faraday's law in another dimension and see how another way we can represent the mathematical form of the law. So watch out for the derivation of an equation for finding the motional EMF to explain Faraday's law. Then make sure you also acquire the skill of using the equation for the motional EMF to show that the induced EMF is the closed electric line integral. Look at this scenario. We have two magnetic poles, the south and then the north. If we have the south here and the north here, then the magnetic fields are moving from the north to the south. This is an imaginary plane that I've placed in the magnetic field. We can ignore it. But look at this electron that is traveling into the magnetic field. Until it experiences the magnetic force, it will be moving in the horizontal direction. But as soon as it enters the magnetic field, it changes its trajectory. The trajectory will change. Thus, if you use the left-hand rule, you should be able to determine that the electron will be moving downwards. As it moves horizontally, magnetic force will also be pulling it downwards. The magnetic force on this electron can be calculated using this formula. You just have to revise. We've come across it before. It is moving with the velocity v. The magnetic field strength is also given as h. So the force will also be a vector, the magnetic force. We are using this subscript to indicate that it is a magnetic force. And if the velocity and the magnetic field are perpendicular, then we can use the left-hand rule to determine the direction of the electric field. Assuming the electron were living in a piece of conductor, and the conductor is rather moving. The conductor is moving into the field, carrying the electron. Then the electrons will experience the force within the conductor because they are free to move within the conductor. And they will move downwards. The electrons will experience the force and move downwards, as you can see here. So many electrons within the conductor will be drifting downwards, and there will be excess electrons at the bottom here and excess protons on top here, or positive charges at the top here. Thus, there will be deficient of electrons at the top here, leaving excess positive charges, and excess electrons here, leaving excess negative charge at the bottom here. There is a magnetic field acting on the electrons. Indeed, there will be similar force acting on the protons to move upwards, but the protons are captured within the center part of the atom, so they will be difficult moving. Except that because this side will be deficient of electrons, there will be excess positive charge at the top end of the piece of wire. Now, if there are excess electrons here and excess positive charges here, then there will be an electrostatic force of attraction between the two charges. The electrons will feel electrostatic force that is given by Q multiplied by the electric field. What it means is that once there have been separation of charges, then uniform electric field is set up within the conductor. It will look much similar like this one. Positive charges are separated on one plate, and the negative charges are on another plate. Then they will create a uniform electric field within the gap. That's what is happening here. Positive charges are accumulating here, and negative charges are accumulating here. So there will be electric field set up within the conductor. So with a force, the force that will be acting on any charge within the field is given by the charge multiplied by the electric field that has been set up. Now the electrons will continue to drift until the electrostatic force is equal to the magnetic force that is drawing them down. The electrostatic force is trying to pull the electrons up because positive charges are here and trying to draw it up. And the magnetic force is also trying to draw it down. There will be a time where the forces will be balanced and the electric force will be equal to the magnetic force. So if we have the electric force being equal to the magnetic force, then we can equate this expression with this and cancel out all the Q's. The equation that no longer depends on the number or the amount of charge. Therefore, we have the electric field being equal to the velocity cross the magnetic field. But we also know from a uniform electric field that the voltage across the plates, that's the voltage that could set up the same thing here, will be equal to the electric field multiplied by the gap between the two sides of the charges. In this case, we want to use L, which is the length of the piece of wire, and the electric field. We see here to be a direct multiplication, but in actual fact, the electric field is a vector quantity, so we need to use a vector length, and the multiplication will become, if you are multiplying vector to obtain a scalar product, then we need to dot multiply them. We have this one dot multiplying this one. So what we have here in vector notation translate to this. The D, we are using the length, and voltage, we are assuming voltage is being induced in the wire, so we are using the EMF instead of the voltage. The voltage is across a resistor or a capacitor or something, but we are using the induced EMF. So instead of V, we are going to use the epsilon here. So substituting this one into that, so what it means is that the induced EMF is also as a result of the electric field that is set up. The electric field multiplied by the distance of separation. If we should have a short element, here, then the induced EMF will be very small. This is a short element here. Then the induced EMF will be very small. Now, if we now consider a whole coil from here all the way to this side, then we need to integrate, or we need to add all the small pieces together. In that case, we are integrating, we are adding the small fields along the loop. Then we are actually integrating along the loop. So the induced EMF becomes the line integral, the closed line integral. Here we are talking about a small piece of the whole conductor. That one will induce a small EMF. But if you want the total EMF, then we are going to have the closed line integral across this one. Thus, we integrate this side to have epsilon, then we integrate this side to also have what we have here. This one we call the closed line integral. This whole thing here becomes the closed line integral. Okay, so let's summarize what we've done. The motional EMF has taken us to a point where we can equate Faraday's law, the basic Faraday's law or the general Faraday's law, to the closed electric line integral. If you remember, you cast your mind to where we spoke about line integral. It was about the magnetic field in the case of Ampere's law. So it was the closed magnetic line integral. Now we are having a closed electric line integral, and that one will give us induced EMF. So we can now equate this. We can now equate this expression to this expression, and that will give us the new Faraday's law that we are going to use in our subsequent lectures. So just go through this lecture again, and we'll come back to see how Maxwell also added some important bits to the whole equations we've been speaking about, and finally write down the Maxwell's equation.